Hello, welcome to day 7 of learning ML from chatgpt. So let's get started. So let's see what today's lesson is. Yesterday we learned about L1 and L2 regularization and also dropout. This was to ensure that there wasn't overfitting or underfitting in our neural network. So please give me day 7's lesson. Okay, so introduction to neural networks, I think it said. Concepts, what is a neural network? Okay. I think we've already gone through part of this though. Okay, so what is a neural network? Neural networks are a class of machine learning models inspired by the human brain. They consist of layers of interconnected nodes called neurons, which process input data and learn patterns to make predictions. Neurons, the basic unit of a neural network, similar to biological neurons, that processes input and passes the result to the next layer. Layers. Input layer receives the input data. Hidden layers, intermediate layers where the network processes and learns from the data. There can be multiple hidden layers in a deep neural network. So assume the more hidden layers there are, the more processing will go on, it means it will take longer, but the better the model will be. And the output layer produces a final prediction or output. Weights and biases. Weights are parameters that adjust the input's significance, and biases are added to the result to shift the output, helping the model learn more complex patterns. So 2. Activation functions. Purpose. Activation functions determine whether a neuron should be activated or not. They introduce non-linearity to the model, allowing it to learn and model complex data. Common activation functions. Sigmoid outputs values between 0 and 1, useful for binary classification. ReLU, rectified linear unit, outputs 0 for negative units and the input itself for positive units, commonly used in hidden layers. TAN-H, outputs values between -1 and 1, used when the output needs to be centered around 0. Softmax converts logits, raw model outputs into probabilities that sum up to 1, used in the output layer for multi-class classification. So that's what we did on the MNIST dataset for the handwritten digits. That's how, and yesterday, so originally we had 91.5% accuracy, then with the added L2, no, it was a dropout of 50%, we got 98.21% accuracy, which was amazing. Forward propagation process. Forward propagation is the process by which input data passes through the network layers, which each neuron applying its weights, biases, and activation function to produce an output. So it's basically just go through the model. Okay. The input data is fed into the input layer. Weight and bias application. Each neuron multiplies the input by its weights and bias. Activation. The result is passed through an activation function. So this decides whether the neuron will be used or not. Activated or not. Output. The final result is produced in the output layer, which is used for prediction. I'm just gonna please explain more. What do you mean whether or not the neuron is used? Activating neurons. In the context of neural networks, when we talk about activating a neuron, we mean deciding whether a neuron should contribute to the network's final output. This decision is made based upon the input. If we didn't use activation functions, the output of a neuron would just become a linear transformation of the input. Okay. For example, if you have an input x and a weight w and a bias b, the output would just be wx plus b. Okay, simple, just a gradient and y-intercept of a line. Problem: a model that only uses linear transformations can't capture complex patterns in the data, no matter how many layers you add. The entire network would still be a linear model. This limits the network's ability to explore more complex tasks like recognizing images or translating languages, because such tasks require understanding nonlinear relationships in the data. Introducing non-linearity with activation functions. Activation functions introduce nonlinearities in model by. Okay. This allows network to learn. Okay, suppose a neuron in your network computes Z equals WX plus B. Instead of just passing Z into the next state of activation, decides how much of X should be passed on. Activation function ReLU. Output Z if Z is positive and 0 if it's negative. The activation function is if the activation function is sigmoid, it compresses Z into a range between 0 and 1. So, is it actually deactivating, or is it just changing a bit so it's just non-linear? So, is this actually deactivating a neuron, or is it just changing it based on the activation function so that the data is not linear? Okay, I'm just going to keep reading through this. Activating a neuron, what it means. Activating a neuron means that the neuron is producing output that is passed on to the next state. For example, if you use ReLU activation function, neuron will activate, I pass on its output. Oh, okay. Neurons out. Oh, okay, so I get it now. Yeah. So 0. Yeah, okay. The higher the number means, I guess, more like weight, kind of. Wait, so I understand that bit now. So when passing on a value in the ReLU activation function, does the value have any effect except from when that value is 0? I assume 0, the model would just ignore it as it's just not relevant. Wait, I'll just ask that question later. Selective activation. By selectively activating neurons, the network can focus on important patterns in the data while ignoring irrelevant ones. Nonlinear decision boundaries. The use of activation functions allows the network to create complex nonlinear decision boundaries that can separate different classes in the data. This is crucial for tasks like image recognition, where the difference between classes is not just a simple straight line. So without activation functions, the network would just be a linear model incapable of handling complex tasks. So if the ReLU activation function just passes on 0, that neuron will be ignored. Right? Okay, in summary, without activation functions, the network would just, network can capable of learning complex tasks by activating neurons selectively based on the inputs, which allows model to capture nonlinear relationships in data. So when we say an activation function determines whether a neuron should be activated, we mean it decides if the neuron's output should be passed on to contribute the final decision of the network. This decision-making process is key to the network's ability to learn and make accurate predictions on complex data. I'm just going to ask this question as well. Yes, that's correct. Let's break it down a bit more. So ReLU. Oh yeah, that's a nice way about going through it. Okay. It's defined as if the input Z is positive, ReLU will just return Z. If it's negative, it will just return 0. What happens when passing through ReLU? Positive values. If the input is positive, forward unchanged. This means the neuron is activated and outputs will influence the next state of the network effects. The larger the positive value, the greater the influence that the neuron has on subsequent layers. Okay. Thus, not only does the neuron get activated, but its specific output value plays a role in determining the overall output of the network. Negative values. If the input is negative, turns 0 effect. A 0 output means that this neuron effectively shuts off or gets ignored for that particular forward pass. It doesn't contribute to anything in the next layer. Okay, one thing I want to know is when you refer to Z, how do we get that Z if it is to have greater influence to the subsequent layer? Generally, are there many layers with different activation functions? How do we get Z? How do we get that Z in the first place? Okay, I'm just going to keep reading this. Yeah, so key points on neuron activation. Ready activation performance. When ready outputs positive value, the specific value wherever it is important because it directly affects the next layer. For example, if one neuron outputs a large positive number, it will have strong influence on the neurons in the next layer. Ignoring neurons. When really outputs, the neuron is essentially output 0 is essentially ignored in the sense that it doesn't contribute to the network's output for that forward pass. This ignoring helps introduce sparsity in the network, making not all neurons active at once. This sparsity can help make the network more efficient and reduce the likelihood of overfitting by focusing only on important features. In summary, ReLU does more than just check if a neuron should be ignored. If the value passed is positive, the neuron is activated and its value directly influences the output. If value is negative, the neuron outputs 0 and is effectively ignored, contributing nothing to the next layer. Okay, great question. Let's break down how we get that Z value and how it fits into the larger picture of a neural network with multiple layers and activation functions. So in a neural network, Z is the input to a neuron before applying the activation function. Here's how we calculate it. Okay. Just with the weights. I get it. Okay. Each neuron in the layer receives an input from neurons in the previous layer. These inputs are multiplied by weights that determine how much influence each input has. In addition to the weighted sum of the inputs, a bias term is added. This bias helps the network learn better by allowing the output to be shifted up or down. Okay, activation function is it. Once Z is computed, activation function, this is where it comes into play. For example, influence on subsequent layers. Output of activation function. The output from the activation function, which is based on Z, becomes the input for the next layer, where this is where the influence comes in. Larger Z values after a larger Z after ReLU or any activation function means a higher output, which will have a stronger influence on the neurons in the next layer. Propagation through layers, the output from one layer becomes the input for the next. Multiple layers, okay, I get that part. So in a deep neural network, you typically have many layers, and layers might use different activation functions. Okay, hidden layers. These often use ReLU, sigmoid, or tan-H functions. The output from these layers continues through the network and influences the next layers. Output layer. The final layer might use a different activation function based on the task. Sigmoid, binary classification, softmax, multi-class classification, and any activation, no activation. Sometimes using the regression task where the output can be any real number. Putting all together. Input layer, raw data fed into the layer, which is multiplied with weight and to bias to calculate Z. Hidden layers, Z values are passed through activation functions like ReLU, and the output influences the next layer. Output, the final activation function produces the network's prediction. Okay, just going to read the summary real quick. Z is the weighted sum of inputs plus a bias, and it serves as the input to the activation function. Okay, the activation function transforms Z, introducing non-linearity, and the output is passed to the next layer. The influence of a neuron on subsequent layers depends on the value of Z after it passes through the activation function. The network adjusts weights and biases across many layers to learn complex patterns with different layers, possibly using different activation functions to achieve the desired test. This process allows neural networks to learn and make predictions by gradually refining how it processes and transforms data through multiple layers. I'm just going to recap what the layers did. So sigmoid outputs values between 0 and 1. Okay. ReLU rectified. So this was one we just looked at. Values between 0, -1 and 1 used when the output needs to be centered around 0. And softmax converts Logit's raw modeling outputs to probability sum up to 1 used in the output for multiclass classification. So sigmoid, binary classification, softmax, multiclass classification. This one, I see. This is mainly used, I assume, in the hidden layers, so to speak. And I would also assume that for TAN-H. So for propagation, we've already read that. So we'll implement a simple feedback feed-forward neural network for binary classification using both TensorFlow and PyTorch. Yeah, so I forgot to ask it up to do only PyTorch this time, but we can still go on. So here we're creating dummy data, random. So I think there's 1,000 elements of 2. No, we're not. It didn't explain the code. Please explain this code line by line. I'm just going to go back to it quickly and just read it through. Okay, so we're getting random X train and we're giving a relationship from the X train to get the Y train, so that it is possible to train a model on it. MP where X train plus X train. Okay, this seems like one for ReLU, yeah, because we're dealing with 1 and 0. So this is like the condition, I assume. And then this is if it is true and if it's not true. Okay, sequential. So we're having one dense layer of 8. 8 neurons, if I can just... 8 neurons and ReLU activation. Okay. Output layer with 1 neuron and sigmoid activation. So this is, if I remember correctly, for binary classification. Yeah, because we're only doing 1 and 0. And we're adding the add-on optimizer, loss, binary cross entropy, and metric accuracy, like we've seen over the past few lessons. Model fit. We're fitting X train and Y train with 10 epochs and batch size. This is like what chatgpt has been using throughout all of these lessons. So X test equals okay, so we're just generating random dummy test data. So I assume this is 1,000 elements of shape, and they've got a shape of 2. So like 2 elements, and oh, okay. Then we're having 5 elements with 2. We're going to predict X test, and we could find that. So I'm just going to copy paste this. And I'm also just going to copy paste this Y train. Copy. Oh, why did it copy the whole thing? So I just want to copy selection. Yeah, there we go. X, Y test. So it's important here that there is an actual relationship, so we can actually predict the model. I'm just going to wait for this to load. It shouldn't be huge as we've got very little neurons, but we are having 10 epochs and batch size of 32. Does it say which? Yeah. Okay, yeah. Okay, So I'm just going to go for I in predictions at 0, print I. And then I'm also going to print Y test at I. I'm going to have to do it in range len. I think this is right. And it would be predictions. Why did I add something on there? What's happened? What if we just do see if this works any differently. Okay, so I'm just going to comment this bit out so the only output is okay. So first one is a prediction, and this second one is the actual. Prediction, actual, okay, let's see. Okay, add, so comma is okay. I'm just gonna add one thing good about Python is the implicit space with the comma. So let's see what we got. So we got this one right, this one right. You know, I'm just going to. How do you round? Okay, I can just do it as it's only for 5. So this one's true, false, true, true, true. Okay, so we see they're mostly accurate, bar 1. So that's not too bad. I'm just going to reread through this. So we're fitting it with X train and Y train. And then we're creating another random set, and we're also making another random set, which is what we're going to compare the results to. So let me see. Import gross data set of 1,000 samples with 2 features each. The values are known. No, the values are random numbers between 0 and 1. Y train creates labels for binary classification. It sums the 2 features for each sample. If the sum is greater than 1, it's set to 1. If it's less than, it is set to 0. So having a dense layer, 2 dense layers, 8 neurons, input shapes 2, because we had a random one of like 2 features, and we're having activation is relu, and then the second one, sigmoid, to get it 0 to 1, which is what we saw, adds another dense layer 1 neuron. Uses a sigmoid activation function which outputs a value between 0 and 1. This is ideal for binary classification since it reduces probability. So we're compiling it, adding an optimizer which adjusts the learning rate during training to find the optimal weights. This loss function used for binary classification, it measures how well the model's predictions match the true labels. Okay. Specifies what we're going to track accuracy as model trains, which measures the proportion of correct predictions. Okay, then we're fitting the model, H-train, Y-train, epochs, and batch size. Next test, 5 new samples, predictions, and we use the model to predict it and printing it. Okay, so we created a simple binary classification problem with random data. Model definition, we defined a small neural network with one hidden layer and one output layer. Compilation, we prepared the model for training by specifying the optimizer, loss function, and metrics. We trained the model on the generated data. Finally, we tested the model by making predictions on new data. Okay. So what was our assignment? Implement basic, use any small data set, build train, try expansion. Okay, I'm just going to ask chatgpt to now please rewrite this code so that it shows the model's accuracy. Just as a simple add-on. So X-train, Y-train, X test, Y test. Okay, so having 200 samples this time instead of 5, so we can get a clear idea of the percentage that are correct. Okay, I'm just going to quickly see. Sample model.predict. Plus 5. Loss accuracy. Okay, so model.evaluate is how we can get the accuracy. If I just add, can I do this? Will it work, or there will be like name versions? Okay, this is only 84%, so I'm gonna try softmax. I want to see, although this is used for multi-class classification, I want to see how it would compare to just using it for binary classification. Yeah, so we see it's almost halved. Then go back to sigmoid. Yeah, so we can see it's changing every time, but we had 84 and 79. What if we use something different to relu? What if we used, what's the name of the other one we had? It was the one between -1 and 1. Oh yeah, tan H. And we'll see what this one gets us. 80, okay. I'll rerun this again and see if we... 84, oh, that's the highest result we got. Yeah. Okay, but I do think relu is still the best, as the data set in which we have, like the values are only 1 or 0, which is perfect for relu, as that's literally what it does. If it's positive, returns 1. If it's negative, returns 0. So relu doesn't actually change anything in it. So actually, then It's pretty pointless. Okay. What if we try using like sigmoid or softmax here? What will the... Oh, okay, 52. Looks like we're hovering around the 50% mark with softmax. 82.5, that's a huge improvement there. But it's all just random data, and you probably just got lucky there. Now what if we change this to sigmoid again? What if we had... I'm also going to test it out using more neurons. 83? Wow. We had 84 first run. Okay, so we're not seeing too much change. Okay, 57. That is not great. So now I'm just going to put it back to the ReLU, which less than 0, so it's negative number, returns 0, and yeah. Now, what if we go 2 and 1? Will this have any effect? Because I'm just curious. First. No, we're seeing huge decreases in... Probably because... I'm just going to revert it back to 1 and 0. And we should get back to around the 80 mark again. Yeah, 81%. So now if we maybe go to 64 neurons, oh yeah, we are definitely seeing a huge increase at 87. What if we do 128 neurons? Wow, yeah, we can see this is going up exponentially. I don't know if it's exponentially, but it's going up a lot. 512. See if we can get to around 100%, like 99. Yeah, we got 99. Okay, so it wasn't too much based on the activation function, because ReLU was right here. Because it literally didn't change anything, and yeah, it was just the right fit for the model. And let's see if we go to 1024. Like, as it's a relatively small model, like we don't have billions of parameters, we only have 1,000. It can go relatively quickly. Yeah, we're still hovering around 99.50. This may be the limiting 100%. Okay, that's really awesome. Yeah. Okay, so we're getting several 100% now. Okay, 99%. But just as a recap today, so we just learnt more about neural networks. So we had been using them before, but we had more in depth. So activation functions are what we use as we decide whether a neuron will be activated or not. So for example, with a ReLU activation function, if it's positive, it will just spit that back out and pass it into the next layer. If it's negative, just 0. They're basically weights, like whether they're important or not. If it's 0, it will basically just be ignored. Where the higher number, like the Z is, as we saw with ChatGPT, the higher like thing we'll have on the rest of the neurons in the later layers. So that's all for today. We also saw the ones we normally have in the output layer are like sigmoid and softmax. Sigmoid for binary classification, and then we had softmax for multi-class classification. One thing I also want to see is if we have another hidden layer. To be honest, I'm not sure it would do anything as it's the same. and we already had like 99%. We can see that the compile time or runtime is slower, but we just got 100%. What if we change this to tan H? And see what this does. But if we already had it for the first output layer as being around about 100%, I think it will still just be around. Okay, so we actually seen deteriorate in efficiency. Okay, it's definitely a little slower with more layers, as each one has to be internet. Yeah, so it looks like we're just stopping around 98.5%. So what about softmax? Like, we saw it being around 50% earlier on, but what if you have it as an input layer that the layer before was just getting like 100%? Okay, this is seeming to be much quicker than the other tan H one. Let's see. Okay, so this is looking like a bit better than the tan H with the added layer, but it's definitely not needed, I don't think, because softmax is just irrelevant to this dataset, where it's just binary class classification. It's 1 or 0. Okay, and no, oh, okay, so I was just a one-off. So I'm just going to delete this softmax one and run it one last time. We should get around, yeah, 98%. So yeah, I'm just going to read the final closing notes. Yeah, so we did this small data set, and yeah, models performance changes. Yeah, that's what we've done. So thank you for watching today's lesson, and I'll see you in the next one. Goodbye.